There we go. Now it's time. Carrie not even gonna make an appearance at all. Nope, she's not. Okay, so let's take a look at some redox stuff. So most of the time you see this, it's going to be in reference to electrochemical cells, but there's some good reminder that we should do. So we're going to back up a little bit and remind ourselves about the definition of redox and all that kind of stuff. So redox is just short for oxidation reduction. And the idea is that we can figure out what's happening with the reaction by tracking where the electrons go. So some chemical species will give up electrons and some will gain them. And so if we track that transfer of electrons, we can tell what's happening in the reaction. So the fundamental definition of oxidation reduction has to do with electrons. So if you remember this oil rig thing, the key here is remembering that when you say oxidation is loss, you're actually talking about a loss of electrons. Or reduction is gain, you're talking about a gain of electrons. Most of the time when we track things, we just look at the oxidation number, but you don't want to mix those two. So oxidation number, if you're looking at that, oxidation is just when the oxidation number goes up. Pretty straightforward. And reduction is when the oxidation number gets smaller or goes down. But if you remember in this oil rig thing, you have to remember that's about gaining and losing electrons. Now, whenever you have a redox situation, you're going to see both oxidation and reduction occurring at the same time. You're not ever just going to have oxidation and no reduction, unless you're looking at a half reaction, but that's kind of synthetic because we intentionally pulled the reaction apart into two halves. If you look at an overall equation, you should see both, or you will see neither, as in nothing's oxidation number ever changes. So if they ask you which one is redox and they give you a bunch of equations, one way to do that is to just track the oxidation number of each thing and see which one has oxidation number that changes. Okay, so if we want to figure out if it changes, we have to know how to assign oxidation number. So on the sheet that I put in the stream and the one that I posted in Classroom, you have this summary to help you remember what's up with each rule for assigning oxidation number. So remember, not very many things have their own rule, and the key is down here at the bottom. We use the things that we know about and the idea that all of the oxidation numbers add up to equal the charge, which a lot of times is 0. So if it's a compound, it's going to be a 0. If it's an ion, it'll be, plus something or minus something. The rules we do have, O is -2. The only time it's not going to be that way is if you have like some kind of hydrogen peroxide or other peroxide. So each H is +1, and therefore each O has to be -1 for that to add up to 0. Hydrogen most of the time is going to be +1. If you throw it in with a metal, like if you have NaH, now the metal is going to have the positive charge, and then the hydrogen will act like the non-metal in that situation. So it's a metal wannabe unless it's with the metal, and then the metal's like, nuh-uh, I get to be the metal. Halogens are -1. The only thing goofy about this that they might do is stick a couple of them together. So like if you have, I don't know, like CLI, and it makes a compound, only one of those can be -1. The other one has to be positive. And the one that's higher up on the list is the one that's going to be negative. So in this case, chlorine is higher on the list than iodine. So their oxidation numbers will look like that. Doesn't happen very often, but you know, AP tests, they do goofy stuff on purpose. So watch out for that. And then if you have a monatomic ion like Ca2+, then we know its oxidation number is just going to be +2. So I think I have some of these. Let's skip to those and see if we can try or practice writing some oxidation numbers. Here we go. Okay, so if we have a neutral compound, remember we're going to track a couple things. We're going to track the oxidation number, and then we have to take a look at the total just so we can use that last rule, because we know, like here, if it's neutral, that the total has to add up to equal 0. So I have a rule for oxygen that it's -2. We have to multiply by how many of those we have. So -2 times 4 will be a -8. Hydrogen is going to be +1 for a total of 2. And then down here, it's the totals that have to add up to 0, not the individual oxidation number. So to make that work, sulfur has to be 6. And so it's going to be +6. And once we get the totals, we really don't care about them anymore. We're just looking at oxidation number and how it might change. Well, CO2 is also neutral, so it's going to add up to 0. O is -2, so here we have a -4. So that means the carbon has to be +4, and I don't have to share it with anybody. There's just one of them, so it gets to be +4. Here's our peroxide that we just talked about. So this is going to be -1 and +1, so that adds up to 0. Otherwise, it wouldn't work out. For an ion, now the total is going to equal the charge of the ion. But O is still -2, so this is still going to be -8. And then we need something here to make that work out. So in this case, it's going to be a 5. And so the oxidation number for phosphorus in this case is +5. And you can do the same thing when you have 3 substances. It doesn't matter. Here they'll equal 0. Here they equal -1. Just go with what you have rules for, and then figure out what you don't have a rule for. Like here we know we have a rule for O. And K is in column 1, so if it makes a monatomic ion, it would do what all the stuff in column 1 does, make a +1 charge. So here the Mn is going to be 7. So same thing up here. Hydrogen's +1, so we get a +3. And then we can use that to figure out what the carbons have to be. Looks like we've got a -1 right there already. So it's going to look like that. So that's the idea with assigning oxidation number. Either do a quick refresher on those or just make sure you have that rule sheet handy. I would actually probably do both. Do a refresher and have the rule sheet handy. Okay, so the whole point of that, if you don't use it for anything, it's kind of silly because oxidation number is completely made up. It's not a real thing that you can measure experimentally. It's just an accounting system to track what happens to the electrons. So we're going to use that here by writing an oxidation number for each thing. We can tell which stuff has an oxidation number that goes up and which one has one that goes down. So if it's a monatomic ion, the charge is the oxidation number. That's pretty easy. If it's an element, the oxidation number is 0. That's pretty easy. So here we have a -1 and a +1. Over here, we know this guy is going to add up to equal -1. And if you notice, every time we see a permanganate, the oxidation numbers are the same. So you'll sort of see patterns that you're like, hey, was that the last time? Yeah, it's going to be that every time. So -2, and then +1. Like so. So now we can compare one side to the other and just look and see who has an oxidation number that gets bigger. We can see that Mn goes from 2 to 7. That's definitely an increase. And then we'll look for something where the oxidation number goes down. Do we have something where the oxidation number goes down? Oh, you know what? This is totally my bad. I wrote this and I ended up having to switch these yesterday. And so then the water should have gone on the other side. Okay, so this is an example of something that can't happen because both of them go up. That's amazing. Good job, me. So these guys should be reversed in my reaction. Well, let's see if we have better luck down at the bottom one. We got 0, +1, +2, 0. This is what you'd see more in an electrochemical cell where you have two electrodes. One's turning into an ion and one's turning into a metal. And so the copper is going from 0 to +2. So that's going to be oxidized. And then the reduction is the silver, which is going from 1 to 0. So we know that the reduction is the cathode, and then the oxidation is the anode. And so you have the handy expression, an ox, red cat, which I don't know if that's an expression or not, but the way I remember is the two vowels go together and then the two consonants go together. That helps you remember which one is which. Reduction is the cathode. All right, so if we look at that in an electrochemical cell, they might give you a couple of half reactions here. And notice that these are both written as reductions. If they give you a portion of a reduction potential list, you can't just look at that and tell what's what. But if they give you something like, say, here, where they say the silver electrode gains mass. Well, if the silver electrode is gaining mass, it has to be doing this. It has to be going from ion to solid. And so the one that is gaining mass is the cathode, because this is a reduction. And if that's happening, then this must be being reduced. So the one that's gaining mass is the one that's being reduced. So in this case, the cathode is going to be the silver, and then the anode is going to be the nickel. And so they always ask you, like, how does it gain mass? Where does the mass come from? Where does the mass go? All that kind of stuff. Remember, the mass comes from the ions in solution, and they gain an electron to turn into the solid. So you want to say the silver ion in solution is where the mass comes from. If you're talking about the anode losing mass, then you just say it goes into the solution as nickel ion. Don't talk about electrons. Don't talk about the salt bridge. They'll just laugh at you and give you no points. Okay, if you have a different kind of situation, like we do down here, and they give you a picture, you can also determine which one is the cathode by looking at the picture. So the one that is gaining electrons so that the ions turn into a solid will be the one that's receiving the electrons. So the copper is getting the electrons, and then the copper solution is turning into copper to make this electrode bigger. So the one that's getting the electrons through the wire is going to be the cathode. Or if you remember, the electrons go through the wire from anode to cathode. So we know this is the anode, and this guy's the cathode. A lot of times when you see pictures drawn, people always put the anode over here. And so everybody always thinks the anode goes on the left. Doesn't have to be. It's the one that the electrons are moving away from. Now, you're not going to have to draw a picture of a salt bridge, but they can still ask you questions about the salt bridge, like what would be present in here and which way would they be going. So remember, you want to pick ions that don't react with anything. So something from group 1 would be good, like potassium ions and nitrate ions, always a good choice. And so if the electrons are going around the circle like this, like so, then so are all the negative things. So the negative ions are going to go through this thing towards the iron, and then the positive ions will go the other way. So these guys are going to go towards the copper in the salt bridge. How are we doing so far?
Amazing.
Okay. Now, calculations they'll ask you about. Remember, E for the cell is the cathode minus the anode. These little circle guys up here just means the standard. So under standard conditions, which are 1 molar solutions of each and 25 degrees. So if you don't have those conditions, then these calculations don't work. You can use the Nernst equation to figure that out. They don't make you calculate it. It is on the sheet, and sometimes they ask you what happens to the E for the cell under different conditions of temperature or different conditions of concentration. And so you'll see these different cathode and anode concentrations in the reaction. Really, the thing you need to remember is that if both concentrations change by the same amount, in other words, this ratio stays the same, then the E for the cell is going to stay the same. The only time changing the concentrations will change E for the cell is if one changes differently than the other. And then just look at the overall equation. You're going to have like a metal and an ion, and on the other side you'll have another metal and another ion. If you increase the concentration of your reactants, then the reaction is going to go faster, and E for the cell will get bigger. So it's a Le Chatelet's principle thing. So you don't really even need the Nernst equation to solve it. Just know if the reactants get bigger, so does E for the cell. If the products, you make more products, then the E for the cell goes down. Oh, also, if your concentrations are identical, not just the ratio doesn't change, like before if we said it was 2 to 1 and then you double them both, it's still going to be a 2 to 1 ratio. Here I'm talking about if the concentrations are actually identical, like 1 molar and 1 molar. If they're both exactly the same, then messing with the temperature is not going to change E for the cell at all. But if they have different concentrations, then based on the Nernst equation, when you warm up the cell, it actually gives you a lower voltage. So just know that if temperature is going to impact E for the cell, it's going to be inversely related. They don't often ask that, but they might. All right, the other kind of electrochemical cell is one that's not spontaneous, one where you have to apply electricity because the potential is backwards. Like it's not going to make a battery, it's not going to produce a voltage by itself. But if you apply a current, then you can do work and plate out a metal where it wouldn't normally on its own. So there's these equations that are helpful. Charge equals current times time, and then the Faraday constant, which says 1 mole of electrons is 96,485 coulombs. And they'll try to word these things different ways, but there's really only 2 or 3 things they can ask for. They can ask for the amount of charge, they can ask for the number of moles, they can ask for the number of grams, they could ask for how long. So let's say we've got a setup here and we want to electroplate something for a half hour. We're at 2.4 amps and the metal that we're electroplating is copper. If they give you a picture, the giveaway for electroplating is that everything happens in the same container. There's not 2 separate flasks or anything like that. So if we know that charge is equal to the current times the time, current being the amps, so if we multiply the amps times the time, we're going to get the number of coulombs. But notice, it needs to be in seconds. So we're going to have to do 2.4 amps times 30 minutes times 60 seconds in a minute. So 2.4 times all that will give us the number of coulombs. And then we can take that and turn it into grams of copper. So sometimes this will just all be one step. They'll be like, hey, if I do this for 30 minutes, how many grams do I get? In this particular thing, they broke it into charge, and then they are going to ask for grams separately. And who knows, they might do that just to get more parts, A through Q, and so they can give out partial credit. And they have an answer for that when you multiply these 3 dudes together. I don't know where my calculator went. Nobody?
4320.
Oh, if you had said 4321, I would say you're making it up. Okay, so 4320 coulombs. Now, the second part, when we go from the charge to the mass, is stoichiometry. So the way we get from charge to stuff we know how to do things with in stoichiometry is using the Faraday constant. So for every 1 mole of electrons, we get 96,485 coulombs of charge. Now at this point, you need to look at the half reaction for whatever metal you're talking about, and they should provide that. In this case, we have something that looks like this, where the copper is a +2 charge, and it's turning into copper metal. So for every 2 moles of electrons, we get 1 mole of copper. So we'll say 1 mole of copper for every 2 moles of electrons. So we got rid of the charge, we got rid of the moles of electrons. Now we're at moles of copper. We just need to turn that into grams of copper using the molar mass of Cu. So it's like a stoichiometry problem with this little charge equals current times time thing at the beginning. So that would be a fun way for them to do electrochemical cell stuff, especially since you can't draw pictures. So I would not be surprised if that shows up somewhere. Now you can do this whole thing backwards, where they give you a mass and a current, and then they might say, hey, how long do I need to run this to get a certain amount? Which actually, now that I mention it, I think I have one of those. So if we do the same thing, we're still using the copper and all that kind of stuff. How long do we run it to get exactly 1 gram? So now we're still going to start with what they give us, but we want the time in seconds. And so if the charge equals the current times the time, then once we solve this for charge, we know our current, what did they say it was, 2.4 amps. Then we can use it to solve for the time. So we're just going to go backwards on this. We need to divide by the molar mass of copper. Then, since it's still copper, we know that for every 1 mole of copper, there were 2 moles of electrons. And that every time I had 1 mole of electrons, that is equal to 96,485 coulombs. So that gets us our charge. And if charge equals current times time, or coulombs are equal to amps times seconds, if I want the seconds, we'll just do that. We're going to take the charge divided by our amps. And that will tell us how long in seconds. That might be kind of ridiculous, so you might need to change it to minutes or hours or whatever they ask for. So once you get your stoichiometry, that answer goes right there, and then you do a little bit of division. Okay. I think that's what I got. What kind of questions do you have? Things you want to talk about this, or something else you came up against when you're doing your studying? No? You're zoning out big time. Looks like your head is undergoing fusion or something.